Hi, good morning.
Apologies, we're going to talk in English, so very sorry that our Italian is not good enough to speak.
So good morning, my name's Daniel, this is David. We are the D Haus company. First of all, it's a real honour to be here, so thank you to Michele and the team for the invitation. We are two architects. We met initially at university and we've been working together on a project for the last 2 years. So we are the D Haus company, and that is an experimental design and architecture practice. We strive to make complicated things simple. We design buildings, we make products, and we produce art. And we're fascinated by a mathematical formula.
The formula is called the Haberdashers Puzzle, and it was discovered by Henry Ernest Dudney in 1903. It's a hinge dissection, and it's the transformation from a perfect square to a perfect equilateral triangle. It has 8 fixed shapes from square to triangle, and this was apparently a bet in a pub. Someone said to the English mathematician, "I bet you can't make a square or triangle," and he managed to do it, and then he published his findings on the Royal Society in 1903 and challenged anyone to try and work it out, and no one could do this for 50 years. If we fast forward 80 years, my father, Ben-Grungerg, who is an artist, created in 1987 a table based on this formula. And as we've now qualified as architects, we're fascinated by this idea and wanted to take it to another level. So applications of the formula. We started experimenting with product design, day-to-day furniture solutions. The first experiment was to redesign the table. So on the top left, that's the D table. We then had playful ideas and took it to children's educational version, and this led to explore different fields like lighting. Lighting became very exciting because the movement and the colours merged, and it became very interesting. But we're now focusing on the D table, as it's generated most interest for us, and we're going to talk about it in more detail now. I'm going to show you a short movie of the D table.
So to get to this stage, we had to go through a lengthy product development process, and we faced many challenges as we tried to transfer the theoretical mathematical formula into a physical product. Problems arose that we didn't expect, and we had to deal with them as they arose. One of the problems we'd like to talk to you about is the hinge. The first prototype that we made, we used a rigid steel hinge, and this was at the exact point of the formula. Now, in a perfect mathematical world, this was the right place for it, but in the real world, it failed because we didn't expect uneven floors in people's houses, basically. And this led to the table being broken. The steel was so strong that it caused the hinge to break.
So our hinge solution needed to be flexible. So we looked at fabric to begin with But this didn't work as it was it didn't have the rigidity of the steel. So we needed to combine the two properties, the strength from the steel and the flexibility from the nylon. And so we designed a poly composite of two plastics. So we had the two properties working. And then what was interesting is that we adapted the mathematical formula, because in the formula the pivot point is at the perfect point of rotation. We had to move the pivot point, well, the actual connection point, into the formula for it to keep the flexibility.
So we've now sort of completed these product improvements and got new prototypes, and working through these issues we've been able to secure funding through Kickstarter to take the products into shops, and it's now on sale. We're also talking with retailers about taking it worldwide, and as you can see on this slide, we've produced colour versions taking influence from some of the lighting studies on the light products we produced earlier. So the table deals with interior space and functionality, but could you scale this up to become a house? And if so, how would you do that, and what would the table turn into? So if we look at the lessons learned from the sort of 5 lessons that we feel we've sort of learning outcomes that we've taken from the table, the first thing being the connection. That's sort of the way the elements of the table fit together. Then mass production. This is when you're producing furniture, it has to be made on a production line, so the way the elements are made is very important. Then looking at the layout, the way the table sits with its environment. So because it can change shape, it's a flexible piece and it can be a space-saving product. Industrial crossover. So we looked at the hinge and other manufacturing techniques to be able to produce a solution. So that was a real source of innovation. And then movement, as in we need the table to be adaptable and flexible based on the formula.
So to begin our research, one of my professors at university was a fantastic inspirational speaker. His name is Colin Davis, and he wrote a book about mathematics and the prefabricated home. And he looks at the idea of the rejection of the prefabricated home within the wider architectural realm. So in this book, we looked at the 5 houses in greater detail. So the 5 houses based on maths and prefabrication are the Packaged House by Walter Gropius and Conrad Wachmann, the Maison Citron by Le Corbusier, Usonian House by Frank Lloyd Wright, the Wichita House, Buckminster Fuller, and the Sunflower House. The Packaged House by Walter Gropius and Conrad Wachmann was very focused on the connection. So Wachmann was obsessed with the abstract mathematical connection, so much that he actually he didn't care about the way the house, the way you lived in the house. So the aim was to develop a low-cost home, but he was constantly developing the actual building component, and he never finished it because he was constantly improving the connection.
The second house we'd like to look at is Maison Citron by Le Corbusier, and this sort of the lesson from this was mass production. Le Corbusier saw the house as a mass-produced product, and houses looked advanced for their time. They had large factory-style windows, with some of them turning the corner, and an open-plan style of living. This was a standardized product with no ornamentation, gables, or bay windows, and he took influence from Henry Ford's automotive production lines.
The third house, the Usonian House, by Frank Lloyd Wright, looks at the layout. The layout is extremely important. It was built for the average American family, but the actual design was based on the ancient Japanese grid house. All of the houses were prefabs rather than one-offs rather than prefab homes. And you can see the grid. It's a rigid grid, but with flexible walls, opening and closing.
The fourth house we'd like to talk about is the Wichita House by Buckminster Fuller, and this sort of looks at dynamic industrial crossover. The house was made using aeroplane technology, and there was an idea of thinking of the house as an aerodynamic object, the shape allowing for high-speed wind to revolve around the house with little problem. Fuller also found that using existing manufacturing techniques in different ways was a key ingredient to successful innovation.
Lastly, the sunflower house. This house, it basically moves. The house is an upper section that rests on a circular track that follows the sun. It's 15,000 tons powered by 2 motors with a total of 3 horsepower. A revolving house is a challenge to gravity, weight and statics, and the very idea of rootedness. So what we learned from those 5 houses, going back to the connection, mass-produced, layout, industrial crossover, and movement. And we'd like to show you now the house that we designed based on what we've learned, but also utilising the mathematical formula. Before we show you, we just wanted to talk about the potential of a site. So we were invited to Lapland, where in the winter it's freezing cold, but also in the summer, what I didn't know is that it becomes very hot. So the house would need to be designed to adapt to extreme temperatures.
So here's a short animation showing the house from...
Full screen.
Short animation showing the house from the top view, changing from a perfect square to an equilateral triangle.
There's no sound. So here you can see very small windows, high thermal mass, and then it unfolds itself, so the interior walls made of glass become the external walls. So doors become windows, and windows become doors. So it completely unfolds itself to become an open house. Here we see another visualization of the house. So now we can apply the 5 things to our house. So the connection, where Walter Gropius was obsessed with the idea of the connection, we also needed to look and see how the house would connect. We solved many challenges with the way the doors worked, the connection points of the actual house coming together, but we felt that we would like to look into the way someone would live in the house. Where Wachman didn't look at that, we've made a short animation of the way the house moves within it.
So the second thing we'd like to talk about is mass production. Basically, the house is a kit of parts, and it's made from one kit. So that means that, as you remember, we had 8 shapes from the formula. That means 8 different houses are possible from one identical kit of parts. So from a manufacturing point of view, that means you can make savings when producing the house. And that also means, because of the mathematical inherent formula, the house can grow and become modular. That means you don't have to start with all the pieces together. You could start with one piece, and the house can grow as your family grows or your needs change. So to test this idea, we travelled to Sweden to look at the manufacturing process. So you can see here a large Hundiger machine which cuts pieces of cross-laminated timber. We did initial tests showing how the roof of the D Haus could come together, but obviously as with the table, we expect there to be some differences between the theoretical mathematics and the realities of the design.
So if you remember the Frank Lloyd Wright house, the grid, based on the ancient Japanese grid, our grid and our layout is slightly different because it moves. So the formula allows the grid to be dissected into 4 parts, and then is reconstructed, reversed, and turns into a triangular grid, which becomes dynamic. So the grid is always moving for us. Because it's flexible, the house also needs to be flexible. And as the house changes because of the temperatures and the environment outside, it can then track the sun. That means it can generate energy. And also it can become a sundial, and optimizing its shape to be efficient all times of year.
So if you remember with Cheetah House by Buckminster Fuller, that we're talking about industrial crossover here, and that means using innovations from other fields in new ways. So for the D Haus, that means using movement technologies and track technologies that will enable the house to rotate. And also looking to the automotive industry on car doors, male and female connections. Basically, we need to be able to keep rainwater out of a building that's going to be moving and have different openings. So leading on to the movement, so we have mobile homes that move from site to site, but our house moves on its own site dynamically 3 folds. So this is key to the response to the external temperature, but also interacts with its environment. And lastly, we'd just like to show you the final animation of the house with the music.
My baby just cares for me. My baby don't care.
Comedy outtake at the end.
Does anyone have any questions at all?
We've done the first costings between £500,000 and around that. So in euros, around 700,000 euros. Thank you very much for your time.
Yeah, thank you.